Hello, grade 11s. In today's lesson, we're going to be looking at Newton's law of universal gravitation, and we are doing grade 11 exam approach. So without any further ado, let's just get right down to the lesson. So before we can get to tackling the question, these are some few physical constants I want you to understand that will be useful in us tackling the questions. So we have the acceleration due to gravity, which is the small g, and it's always substituted as 9.8 meters per second square. Then we have the universal gravitational constant, the big G, which is always 6.67 times 10 to the power of negative 11, right? Then we won't be using the Coulomb's constant and the charge of electron. These are only used in electrostatic, which is the following topic after this one. Then we have the mass of the Earth, which is 5.98 times 10 to the power of 24 kgs, always substituted like that. And then we have the radius of the Earth, which is always substituted as 6.38 times 10 to the power of 6 meters. So these are all the constants that you'll be using for this topic. Then let's go ahead and check the formulas. Then the first formula that we're going to be using for this one is W is equals to m times g, which is the formula that we'll be using to calculate the weight. It can also be written as gravitational force times is equals to mass times the gravitational acceleration, right? So this we're going to be using it if we want the weight or the gravitational acceleration or the gravitational force, as it says. Then the gravitational acceleration is the one that we spoke about, always 9.8 meters per second square. If we are calculating the gravitational force or the weight of the object on Earth, but then you will notice with other questions, if we are given a different gravitational acceleration, then we have to use that. For example, if we are on planet Mars, then the gravitational acceleration cannot be 9.8 meters per second square. We have a different gravitational acceleration there. So different planets have different gravitational accelerations, right? Or in different satellites, we also have different gravitational accelerations. Then we also have this formula here, so it can be that one or this one, which we can see the only difference is that the first one has d squared and the second one is r squared, which d represents distance and r represents the radius, right? So it can be, the distance can be between the radius or just the distance in between the surfaces. Then here we have the formula. This is the formula of the universal gravitation law formula. So we say its F is equals to G m1 m2 over d squared, or F is equals to G m1 m2 over r squared. Then the last one here, this formula is used to calculate the gravitational acceleration of a particular planet, right? So remember, if we are not calculating, if we are not on planet Earth, say we are on planet Mars or planet Neptune or Jupiter, then we know the gravitational acceleration there is different from the one that we have on Earth. So we calculate using that formula and we get the gravitational acceleration. Also, you can use the same formula. Say if you're given the gravitational acceleration of that particular planet and you are trying to calculate the mass of an object on that planet, or the distance or the distance of that particular object relative to the surface of that planet. One thing that we also need to know with using this formula or these formulas is that your mass should always be in kgs. Remember, we are dealing um with objects that are relatively large, right? So this is in kgs, and then your distance or your radius should always be given in meters. But then you will see with other questions will be given in kilometers, because here we are dealing with greater distances, right? But then always in our formula we must substitute our radius or distance in meters. So every time we are given in kilometers, we have to remember that we have to convert that to meters. Now, how do we convert kilometers to meters? You just simply multiply whatever that you've been given in kilometers by 1,000, right? So, but because we'll be given relatively larger numbers and we don't want to write those big numbers, right? So the easier way to do this is, let's say we are given a distance of 6,300 kilometer, right? And they say this is the distance between planet, let's say they say planet X and planet Y, right? So planet X and planet Y has a distance of 6,300 kilometers. So the best way to write that is just, we want to say 6,300 multiplied by 10 to the power of 3. So we write it in scientific form, right? So you will realize that 1,000 is the same as 10 to the power of 3, right? Because 10 to the power of 3 is the same as 10 times 10 times 10, which we know 10 times 10 is 100, times 10, that's 1,000, right? So that's like the efficient way of writing that, right, without having to write those big numbers and so many zeros, right? So now, with all that being said, let's just get right down to the questions and see what we've got. Then we have question 6. It says the gravitational force on a probe called Curiosity on the surface of Mars is 3,338 newtons. Then they say the radius of Mars is 3,390 kilometers and the mass of the planet is 6.39 times 10 to the power of 23 kg. So let's just go highlight everything that's important here. So we are given the force, the gravitational force, and then we are given the radius of Mars, which is 3,390 kilometer, and we are given the mass in kgs. But then we can see our force, gravitational force, is in Newton, correct as a unit. But then what about the radius of Mars? We are given in kilometers, right? So we have already spoken that we don't want our distances in kilometers. So what we're just gonna go ahead and convert that one, right? So we want to quickly convert that. So our radius is 3,390. Then in order to convert that, we're just going to say times 10 to the power of 3. That will be in meters, right? Awesome. Then everything else is in the correct SI unit. Then 6.1 says state Newton's law of universal gravitation in weight, 2 marks. So whenever you get to these questions, we expect you to know the definition. Usually this is the definition that they mostly ask in almost every question that has to do with the Newton's law of universal gravitation. So Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So word to word like that, that's how you're expected to define it according to your CAPS document, right? Then 6.2 says calculate the mass of the probe. So now we're just going to go ahead and collect our data. As you can see, we've highlighted all our data. So then we know the formula that we have to use here is the formula for the universal gravitation. So which goes F is equals to G m1 m2 over r squared, right? Then remember our big G, this is the universal gravitation, which is always 6.67 times 10 to the power of negative 11. Then what is the mass? We have the mass of planet Mars, which we've been given to be 6.39 times 10 to the power of 23. Then we are looking for the mass of Curiosity, the probe. Then we're just going to go ahead and substitute m there. And then the distance we've been given to be 3,390 kilometer. But remember, converting it, we say times 10 to the power of 3. And then never forget to put that square. But then remember, we've been given the force. So the force is 3,338, right? So at this point, you just want to apply your math. You're just going to go ahead and cross multiply this, right? So after cross multiplying the denominator here with this number here, so that you can write it as over 1, and then cross multiply there, we're also going to divide by the whole of this, right? So you just want to be quick with your maths there, because remember, we're not really concerned about all those steps that you're going to have for maths. We just want to test the skill of substituting into the correct formula and then getting the correct answer. 90 times 10 to the power of 23, and then square. So we've cross multiply that. Then we're going to bring over whatever that we had in the numerator now to be the denominator. So we divide by all that. Then to the power of negative 11, multiply by 6.39 times 10 to the power of 23, right? So 23. Then let me erase here. Remember here we had to the power of 3, not 23. We had that to the power of 3. And then all this is equal to the mass of the probe. So when you punch all this in your calculator, it should give you the mass of the probe, which punching all that in a calculator, we have 900 kg, right? So 900 kg, that becomes our mass, right? Now let's move along. Now 6.3 says calculate the weight of the probe on Earth. So you will remember that we said when we calculate weight, we have the formula there. And you can also see the marks here. We are given 2 marks for that. So that means we just go to calculate the weight. So let's write, so you can write Fg or you can write weight. But I like to write Fg, right? Then the mass is, remember we've calculated the mass already, so it's 900. Multiply that by the gravitational acceleration of 9.8. Then now we have 8,820 newtons. So that becomes the weight of the probe, right? So remember there is a difference between the mass and the weight. The mass is just the amount of matter that we have in that particular object, and then the weight is the force that the center of the earth attracts an object by, right? Then let's move along with the questions. We have question 5 here. It says state Newton's law of universal gravitation in weights. So you can see that that definition popping again. So let's define Newton's law of universal gravitation again states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers, right? Then 5.2 says a man of mass 90 kg. So what is that? That is the mass, right? Is standing on the surface of the earth. Then 5.2.1 says calculate the force that the earth exerts on the man, right? So the force that the earth exerts on the man, remember the force that the earth exerts on the man is obviously the weight or the gravitational force, right? So what we are asked to calculate here is actually the weight or the gravitational force. So we go for that one, we go Fg is equals to m times g. So for this one, we are given 3 marks. So they're going to be marking the formula. And then substitution into the formula, we have 90 and then multiply by our g, that's 9.8. So 82 newtons, right? So that's our solution for this one. Nice. Then let's go to 5.2.2. It says use your answer in question 5.2.1 to calculate the mass of the Earth if the radius of the Earth is 6.38 times 10 to the power of 6. So now we must calculate the mass of the Earth. So for that one, right now we've been given the radius, so we know we have to apply the formula for the gravitation, for the universal gravitation, right? So is it in meters? Let's check. Yes, it is in meters. So no need to convert. So we have F is equals to G m1 m2 over r squared. Then what is our G? Always a constant of 6.67 times 10 to the power of negative 11. Then the mass, remember, we have 90 kg. And then here we are looking for the mass of the Earth. So let's edit it as ME. And then we have the radius we are given to be 6.38 times 10 to the power of 6, right? And then we have square there, right? So you can see that it even corresponds to the radius of the Earth that we have on the data sheet, right? So looking at this, we can almost see that we're probably gonna get even the same mass of the Earth that we have, right? So we have 882 here. Then at this point, again, you want to cross multiply this. So you have over 1 here. You want to cross multiply this and then divide by the whole of that. So we have 882 multiplied by 6.38 times 10 to the power of 6, and then we have square there, all over 6.67 times 10 to the power of negative 11, and then we have 90 here, and then all that is equals to the mass of the Earth, right? So now you just want to punch all that in your calculator. So we have mass of the Earth. When you punch that in your calculator, you have 5.98 times 10 to the power of 24 kg, which it corresponds to the value that we have on our data sheet, on our physical constants, right? So yeah, that is the mass of the Earth. Awesome. Then let's move along to another one. So question 5 again, it says the acceleration due to gravity on planet X is 2.7 meters per second square. Then the radius of this planet is a third, so 1 over 3, 1/3 of the radius of Earth. Then they say 5.1, explain the difference between the weight and mass. Awesome, that is a good question. So now we want to know what is the difference between weight and mass, right? So we know, generally speaking, you hear people saying, I have a mass of 78 kg. I have a weight. Sorry, generally speaking, they say they have a weight of 78 kg, 60 kg. But then in physical science terms, that's not how we say it. Usually the person has a mass of 78 kg, but then when we want the weight, now we have to take that 78 kg, multiply it by the gravitational acceleration. So now we understand that since planet X here has a gravitational acceleration of 2.7 meters per second, a person of the same mass on Earth won't have the same weight here on Earth and also on planet X. Why? Because what determines the weight now, remember, weight is m times g. So what determines the weight is the mass of that particular object times the gravitational acceleration on that particular planet, right? So if the gravitational acceleration is less on that particular planet, then even the weight will be less, but the mass is always constant, right? So a person of 78 kg here on planet Earth will still be 70 kg on planet X, right? But then what will be different now? His weight won't be the same, right? Why? Because the gravitational acceleration is not the same, right? So generally on planet X, it would feel like it's lighter, but then on planet Earth, it would feel heavier because the gravitational acceleration on Earth compared to the one on planet X is way greater, right? Then let's look at the difference between weight and mass in terms of the definitions. So we say the mass of an object is the amount of matter in an object, right? So it's how much matter that object has in it. Then, but the weight of an object is the force with which the center of the planet attracts an object. So that is where now we take that mass times its relationship with the gravitational acceleration, right? So that's the difference between weight and mass. That's how you should define it according to your CAPS document. Then 5.2 says calculate the mass of planet X. Then how do we calculate the mass now of planet X? So again, let's see all the info that we've been given. So we are given the gravitational acceleration, which now you can see which formula we can use. Remember, for the gravitational acceleration, when we are given that, that's where now we can use that formula with G. Then we have 1/3 of the radius of the Earth. So let's run quickly. Now we are looking for this formula. We are looking forward to use this formula Gm over r squared. Then we are given the gravitational acceleration. Remember, you won't substitute 9.8 because we are not on planet Earth, right? Then our G is 6.67 times 10 to the power of negative 11. Then what are we looking for? We are looking for the mass, right? So we're just going to substitute that m. Then we've been given the radius to be 1/3 of the radius of Earth. So it's 1/3. Then the radius of Earth, we know it to be 6.38 times 10 to the power of 6, right? According to our data sheet, right? Then again here you do the same thing. You have to say over 1 here, cross multiply this, and then also cross multiply that. Then you just have to bring over what you have here, the value that you have to be the denominator, right? So you divide by that value. So now we have m is equal to 1/3 times. So okay, let me erase that. Remember what we have there. We have 2.7, yes, and then multiply that by 1/3 of the radius of Earth. So remember, you don't want to round off anything before you get to the final answer. So which is why I'm like showing you all this so that you just punch everything all at once in your calculator to avoid the rounding off of values. Then 6.67 times 10 to the power of negative 11. It's only on the final answer whereby you are allowed to round off to at least 2 decimal places. Then we have punching all that now in your calculator. So now we have 1.83 times 10 to the power of 23. Then remember, our mass is always given in kgs. So that's your value. That's your value. Then let's check 5.3 for 2 marks says determine the factor by which the weight of an object on planet X will differ from the weight of the same object on planet Earth. Now remember what I said. I said on planet, if the person is on planet Earth, they will have the same mass. So the mass is always constant, but then the weight is not the same because the weight now has to correspond to the gravitational acceleration, right? So it is determined by the gravitational acceleration. Now we want to check by what factor will they differ, right? So that means what we are trying to compare here is the gravitational acceleration of these planets, right? So now in planet Earth we have 9.8, but then in planet In planet X we have 2.7. So this is what we're going to have. Let's put it like this. So let's say this is planet X and this is Earth, right? So on planet X, what is our G gravitational acceleration? Is 2.7, and then here we have 9.8. So in order to get by what scale factor does it differ, we can just divide both sides by 2.7. 2.7, then we have 1 is 2, 3. So put that in your calculator, 3.63. Planet X is 3.63 times smaller than planet Y, right? So the weight, in planet X will be 3.63 times smaller than in planet Earth, right? Than in planet Earth. So in other words, that is to say, the same object would feel much heavier on Earth than it would in planet X, right? Now let's look at another question. It says an object of mass 200 kg. What are we given there? So our 200 kg is our mass, and then orbiting the Earth at a distance d, so we are not given, from the Earth's surface, the weight of the object at that position is 10% less than its weight on the Earth's surface. What we are experiencing is that as the object is going higher, its weight will be much lower than its actual weight when it's on the surface of the Earth, right? Then 5.1 again says state Newton's law of universal gravitation in words. So you can see that definition is appearing more and more. So you need to note that. You always have to know that. Then we say it's Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. So that's it. Awesome. Then let's look at 5.2. For 7 marks, we are asked to calculate the distance d from the Earth's surface at which the satellite is orbiting. So no need to worry. Remember, we said 7 marks doesn't tell us about the difficulty of the question. It only means that we need to calculate other values before we can get to the actual value that we are looking for. So for example, here we need to first deal with the fact that they said that the weight of the object at that position is 10% less than its weight on the Earth's surface. But then here, before we can find that 10% difference, let's now calculate the actual weight when it's on the Earth's surface, right? So we have 200 kg, and then we know to calculate the weight, we have Fg is equals to m times g, right? Remember, weight is the same as the gravitational force. Then we have 200 here, multiply that by 9.8, then we have 1960 Newton. So this is 100% of all the weight, right? But then remember, they say as that object is moving farther away from the Earth's surface, its weight is becoming less up until it reaches a point whereby now it is 10% less than what it was on the Earth's surface. So now if it's 10% less than what it was, that means at that position, now this object is 90% of what or of its actual mass on the Earth's surface, right? So we can just say 1960 times 90 over 100. So you can see with that 7 marks that we still need to calculate a lot of values along the way before we can get to the actual value. So that's 1764 newtons. So Again, there is another way which you could have done that. You can just say 1960, multiply that by 10 over 100 just to find 10% of that. So if you find 10% of this, that's 196. Then obviously to get to this one, you'd have to say 1960 minus 196, right? Then also that one would still give you 1764, right? So still the same approach. You can find what is 10% of that and then subtract it to the original weight, or you can just calculate 90% of that, because if it's 10% less, that means now it's 90%, right? So two ways to deal with that. But then now let's continue. Now that we have the weight, we can now calculate the distance. Remember, we have the formula F is equals to G m1 m2 over r2. The force here, remember, is the gravitational force, as the formula states, right? So that is the gravitational force, which is the same as the one we just calculated. So we have, now we put 1764 because at that position it is now a 90% of the weight it was when it was on the Earth's surface. Then here we have the G 6.67 times 10 to the power of negative 11. And then what is our mass? We have 200 for the object. And then this is interacting with the Earth, right? So the mass of the Earth constant is 5.98 times 10 to the power of 24, right? Then all over, are we given the radius? That's what we are asked to calculate. So the distance, they want the distance. Let's check the question. It says calculate the distance d from the Earth's surface at which the satellite is orbiting, right? Which the satellite is orbiting. So now at this point, in order to calculate a value that is here, which is d or r, so let's edit this one. This one will also be d squared, right? Then in order to calculate this one, we'd have to cross multiply here. But because we are looking for the value here, the easy way is just to swap the values here. So bring this over here and take that one to that other side. So it's the same thing as cross multiplying, but then because you're looking for this value, you just swap the values like that. Then let's check. So in other words, here we have d squared, and then whatever that was up there, we just keep it like that, 6.67 times 10 to the power of negative 11. And then we have our 200. And then we have our 5.98 times 10 to the power of 24. And then remember, now we are bringing over here 1764. At this point, we can see that we are looking for d, not d square. So we can just square root both sides, square both sides. Then we have d is equals to 6.7 to blah blah blah, whatever the digits that we have there, times 10 to the power of 6 meters. So at this point, I'm not rounding it off, so I'm just going to save it as answer on my calculator. Then remember now that this is interacting with the surface of the Earth, right? We have to subtract the radius of the Earth from the distance, right? So this distance, we are saying this is the distance whereby we have the radius of the Earth plus the distance of the Earth's surface and that satellite. So now in order to check for the distance between the satellite and Earth, we have to now subtract the radius of the Earth, which is 6.38 times 10 to the power of 6 meters, right? So subtracting that, our distance is now, so d now becomes 3.45 times 10 to the power of 5 meters. 5.3 says the object is moved to a new position where the distance from the center of the earth is twice the radius of the earth. Now they say write down the mathematical relationship between the weight of the object and the distance at which it is placed from the center of the earth. So here we are looking at the relationship between the weight and the distance. Now you will note that we do have this relationship from the definition. Remember, it says where the gravitational force is directly proportional to the product of the masses and inversely proportional to the square of the distance in between their centers. So inversely proportional. So a mathematical relationship, this is how we show that. So for inverse proportion, we say F is inversely proportional. So inversely proportional, you're gonna have 1 over the quantity, so d squared. So this is the weight or the gravitational force is inversely proportional to the square of the distance between their centers. So that is the mathematical relationship. You show it like that. So if it is the mathematical relationship, just for interest's sake, if it is the mathematical relationship for the gravitational force or the weight with the masses, you just say F is directly proportional to the masses, so M1 and M2, like that. So you can say with directly proportional, there is no fraction there. So it's just F directly proportional to M1 multiplied by M2. But with this one, this is inversely proportional, so we have 1 over d squared, right? Then 5.3.2 says determine the weight of the object at the new position. At the new position. So now let's check. We've been told here that the object is moved to a new position where the distance from the center of the earth is twice the radius of the earth. Is twice the radius of the earth. Now, if we look at this formula here, we have F. Let's look at this formula here. We have F is equals to G M1 M2 over R squared, right? But then they told us something. They said now this is moved to a position whereby the radius is now twice that of the earth, right? So if we can just edit that, we now have G M1 M2, and then here we have twice the radius, right? So we have twice the radius. So it's like that, right? So meaning, in other words, having to punch all this. So 2 to the power of 2 is 4. So we have, let's write it like this. That means now we have 1 over, we have 1 over 4, right? And then this is still G M1 M2 over R squared. So this is the 2 square here, giving us the 4, and then the 1 here from the constant. That means now the F nu in this case, the F nu in this case is 1 over 4, 1 over 4 of the F old, right? So this is 1/4 of the F old. So now what we can do is, we know what is the F old, right? So we're just gonna say F new. It's gonna say 1/4 times, but we did calculate that one to be 1960, right? Remember, at that position when it was still on the Earth's surface, right? So it's 1 over 4 times 1960, and then when we multiply the 2, we get 490. So 490 newtons. That becomes our solution for this one. Awesome. Now we have question 6. It says passenger plane accidents are becoming very common. In one recent accident, an Airbus with a mass of 30,000 kg, so 30,000 kg, that becomes our mass, was last seen on the radar at a height of 3,500 meter above the Earth's surface before crashing into the sea. It is not yet clear what caused the crash, but some reports allegedly say that the plane exploded before hitting the water surface in the sea. Right. Then 6.1 says, name and state the law that explains the force with which the Earth and the plane interact at a height of 3,500 meter above the Earth's surface. So we know obviously what law we are talking about here. For 6.1, we are talking about the Newton's law of universal gravitation, which states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers, right? So 6.2 says, now how does the magnitude of the force experienced by the plane compare to the force experienced by the Earth due to this plane? Only answer greater than, equal to, or less than. So we know, according to our Newton's third law here, we know that when the plane exerts a force on the Earth will also exert a force of the same magnitude, but in opposite direction. So that means the correct answer here is obviously equal to, right? Then 6.3 says, explain why the plane can be seen moving towards the Earth and not vice versa. Why we don't see the Earth moving towards the plane, but we are only seeing the plane moving towards the Earth. This has to deal with the relativity of the masses, right? So obviously we are bound to see an object of a smaller mass moving as compared to seeing the one that has a lower, a greater mass, right? So the one with relatively a smaller mass will be the one that we see moving. So we say the mass of the Earth is so much greater than the mass of the plane. Hence we see the plane moving towards Earth and not the Earth moving towards the plane. So 6.4 now says, calculate the force exerted by the Earth on the plane at a height of 3,500 meters. Now pause there. Remember what we spoke about, right? We said if the Earth is interacting with an object that is inside Earth, then what do we have for the distance? This is where now we have our distance, or our distance being the radius of the Earth plus the distance in between the Earth, the surface of the Earth, and that particular object, right? So we can see that we have that case here. The plane is obviously inside Earth, so we have to take the distance that we are given, 3,500, but add it to the radius of the Earth, right? So now let's go. So for 6.4, we have F is equals to G m1 m2 over r squared, right? Then what is our G? We have 6.67 times 10 to the power of negative 11, right? Then the mass we are given that the mass of the plane is 30,000, right, kgs. But then this is interacting with the Earth, which has a mass of 5.98 times 10 to the power of 24, right? Then we are given here, so we can just edit this one. We can just edit this one so that we see this is R E plus R and then square, right? Because we have an object interacting with an object inside Earth interacting with Earth, right? So what do we have here? The radius of the Earth is 6.38 times 10 to the power of 6. Then add that to the distance that we are given between the plane and the surface of the Earth. Then square that. Then punching all that in your calculator, you have 2.94 times 10 to the power of 5 newtons, right? And then to what direction is that? It's obviously downwards. Remember, this is gravitational force, right? The F that we are checking here is the gravitational force, so it is always acting downwards, right? It is always acting downwards. So for 5 marks, we have that. Then 6.5 says, with what factor will the force of impact F that the plane experiences on the surface of the water change? If the planet had to crash on a different planet, we double the mass with what? Double the mass of the Earth and the total distance a third of of the Earth. So we are given here double of the mass of the Earth and a third of that on Earth. Show calculations. So now let's check again. Let's see the original formula. The original formula, we have it as F is equals to G. Let's say this is the mass of the mass of the Earth, and this will be the mass of the plane, right? So what are they saying here? So they say, with what factor will the plane experience? So mass of the plane, yes. Then over, so we have r squared like that. Then remember, what did they say? They say double the mass of the Earth. So I'm just gonna go ahead and say 2 times me, and then my m of the plane is still the same. Then they said 1/3 of the radius, so I have 1/3, and then r, and then square that, right? So now what do I have? If I have this 2 here, so let me write it here. So I have this 2 here, and then over, I have this 1/9 from 1/3 square. And then my formula is still going to be the same. I have mass of the Earth, mass of the plane, and then now here I'm left with r squared. But remember, this formula here is for F, right? So that means in this case now I have what? I have 2. So in this case, I have 2 over 1/9, and then all that to F, right? So if we just deal with this, we know that here we have 2 times 9/1, which and then F, right? So remember, we can just do reciprocal for that. Then 2 times 9 gives us 2 times 9 will give us 18. So our solution is 18F. So that means whatever force that you have will be 18 times, right? Now let's look at this one. So 6.1 says, state Newton's law of universal gravitation in weights. Again, we can see that that definition. So by now we probably know that definition by head, right? So it's Newton's law of universal gravitation states that every particle in the universe attracts every other particle with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers, right? Then 6.2 again says, distinguish between the mass and the weight of an object. Let's go again. We say the mass of an object is the amount of matter in an object, and the weight of an object is the force with which the center of the planet attracts an object. So remember, with these questions, I'm doing so many questions so that you can see the trend of the questions, see how they ask the questions in an exam, and which questions you need to focus on, and which questions you need to focus on, and which questions you just need to just browse through them, right? So this is only to show you the trend of questions. The reason I'm doing so many multiple questions is just so that you know how to study for this topic, right? Then 6.3 says, during a lunar eclipse, the Earth, the Moon, and the Sun are aligned on the same plane as shown below, right? Then 6.3.1 says, using the data given above, calculate the magnitude of the force exerted by the Moon on the Earth. Exerted by the Moon on the Earth. So we can see that we are given there. We are not supposed to use our data from the table that we have on the back of the question paper, but we are given the data here. So note it's saying using the data table given above, not anything else. So we are given that. Then it says calculate the magnitude of the force exerted by a moon on the Earth. So we are also given the distance between the Earth's moon and the Earth. So remember, everything here is in relation to the Earth, right? So the distance that we have here is the Earth's moon and the Earth, and the distance that we have here just below that is the distance of the Earth and the Sun, right? So we can even see from here. We can even see it is indicated here, right? Now let's go ahead and calculate. So we have, so this is how we want to indicate it. So we'll say f of moon on Earth. So I'll just write m on E. So that's moon on Earth is equals to g m1 m2 over r squared, right? So what is my g? Remember, constant 6.67 times 10 to the power of negative 11. And then I have the mass of the moon, 7.35 times 10 to the power of 22. And then the mass of the Earth here, we are given 5.97 times 10 to the power of 24. So you will note that it is not the same as the one that we have on our data sheet. That one is 5.98, but then we are required to use this one. So you don't use that other one. You don't use the one you are given on your data sheet. Now, what is the distance? The distance you are given to be 3.84 times 10 to the power of 8, and don't forget to square that. So you can see here we are not adding also the radius of the Earth. Why? Because here we are comparing two celestial bodies, that is the Earth and the Moon. So the Moon, remember, it's not inside the Earth, right? So having all that, if you punch that in your calculator, we have 1.985 times 10 to the power of 20 newtons, right? So that is the force that the moon exerts on the Earth, right? Now, they're saying the force exerted by the sun on the Earth is 3.522 times 10 to the power of 22 newtons, right? Now, write down 6.3.2 says, write down the magnitude of the force exerted by the Earth on the sun. So remember here we've been given the force that the sun exerts on Earth. Now they want the force that the Earth exerts on the sun. So here, this is where we're going to be applying Newton's third law. When object A exerts a force on object B will simultaneously exert a force of equal magnitude, but in opposite direction. So equal magnitude. That's what we are looking for. That means the force that is exerted by the Earth on the sun is the same as the force that the sun exerts on the Earth. So that for 1 mark, you can see it's the answer to that one is 3 also 3.522 times 10 to the power of 22 newtons, right? So that's it. Now let's look at the last one. It says, calculate the net force experienced by the Earth due to the moon and the sun. The net force. So now we are looking for the net force, right? So now, net force experienced by the Earth due to the moon and the sun, right? So now you can see that we do have the force that the moon exerts on the earth, and we do have the force that the sun exerts on the earth. So at this point we are trying to find the net force, but we can see that they are not in the same direction, right? So now we have to choose the direction. Obviously it is best that we choose right as positive, right? Because that's how we know best. So right as positive, let's indicate. So we are choosing our right as positive. So we start by saying F net is equals to the force of the sun on moon, on earth, meant to say. Then that plus, since we are choosing that, since we are choosing right as positive, so let's indicate right as positive. So since we are choosing right as positive, that other one has to take the negative direction. So plus negative F of moon on earth, right? So this one, remember, is the positive direction, and the force of the moon on earth will be the negative direction, right? Now let's go. That means for this one we have, what is the force of the sun on earth? That's positive 3.5 22, multiply that by 10 to the power of 22, and then we have minus, remember positive times negative is negative, then we have minus 1.985 times 10 to the power of 20, which remember is the force of the moon on earth, right? Then having to subtract it, we now have 3.50 times 10 to the power of 22 newtons. And then we'll say that is moving towards the sun. Remember, it's taking, if it comes out as a positive, that means the positive direction is the one that is bigger. So this one is moving to the right. But to the right is towards the sun, right? So towards the sun. So that's it for this question. All the best. Keep on practicing, guys. See you next time. Ciao.